Ladies and gentlemen, I want to present you the impact of the multiwall carbon nanotubes on the emphatic properties of adhesive joints subjected to peel 2024 aluminium alloy. As we know, the structural adhesive joints are becoming more widely used, especially in the industries where minimization of weight is of the final product is important. Consequently, bonding is commonly used in aerospace and automotive industries. It is commonly known that adhesive joints should be loaded with the shear stresses. Distribution of shear stresses is favorable, and peel is very unfavorable because of this peak of stress, of normal stress. And so now I want to present you results of experiments of improving, especially photic strength of adhesive joints subjected to peel by using of multi-walled carbon nanotubes as the fillers of epoxy resins. Multi-walled carbon nanotubes that we use in experiments were produced in our laboratory with use of the CVD method. In order to achieve it, the ethylene as a source of carbon was decomposed, and here we can see the transmission electron microscopic images that presents our products, our multi-walled carbon nanotubes that have external diameter between 20 to 40 nanometers about. And we used these nanotubes to preparation epoxy adhesive composition, and we prepared this composition in the following sequential stages. The epoxy resins was heated up in order to reduce its viscosity, then the proper amount of carbon nanotubes were added to them. Next, mechanical and ultrasonic mixing of the resins was carried out, and after cooling, the right amount of hardener was added. And we prepared 3 different variants of nanocompositions with different contents of carbon nanotubes. It was 0.5, 1 and 1.5% by weight of carbon nanotubes in epoxy adhesive. And that adhesive composition we used to prepare a specimen of adhesive joints. Static strength tests we conducted with use of T-peel method for the specimen that we see in the higher figure, and below we can see the shape and the dimension of specimen used in photic tests. Both of adherents were made of 2024 aluminium alloy, and surfaces before the bonding process were prepared by mechanical methods. And here we can see results of T-peel tests. Here is a comparison of typical graphs plotted during T-peel tests for variants with nanofillers. It is this red curve, and without nanofillers, it is this black curve. The differences in the shape of the curves confirms that the additions of nanofillers in the form of multi-walled carbon nanotubes has an impact on the increase of the stiffness of adhesive composition. The experiment showed that every variant of joint with nanofillers, for every variant of joint with nanofillers, the value of peak load is significantly greater when compared with a basic variant without nanofillers. Meanwhile, this tendency is inverted in the later stages, where the average peeling force is greater for the basic variant. And now I want to present you the results of fatigue strength, because this is a main topic of this work. The fatigue tests were conducted with use of our proposed methodology, which is a convenient and relatively fast high-cycle fatigue strength test method for testing of adhesive joints subjected to peel at a resonance frequency of specimen. The tests were carried out with the vibration test system, which consists mainly of a shaker and high-speed camera used to measure amplitude of displacement of this point of dynamic bending adherent. Specimens for each variant were subjected to resonance vibration at 4 different amplitude levels, and this vibration induced dynamic bending of adherent, flexible adherent, what is the reason of dynamic peel loaded of adhesive joint. The number of cycles was counted up to the point when it was no longer possible to maintain the vibrations of the specimen at a given amplitude level, which was the evidence of destruction of joint. For every level, the tests were repeated 4 times. The lowest level of the dynamic load was the value at which the specimen did not fail after being loaded by 2 million cycles, and the value of the resonance frequency of that specimen was about 600 Hz. As I said, the amplitude of the end of the flexible adherent was measured with use of high-speed camera, and this value of amplitude was correlated to the maximum normal stress in the adhesive joint obtained by finite element analysis. And when I will talk about fatigue stresses, I will have in mind this maximum volume of stress. During the fatigue strength tests, it was noticed that the value of resonance frequency of the specimen depended on the degree of the fatigue joint failure. We could distinguish 2 stages of fatigue destruction. During the first stage, the value of the resonance frequency decreased slowly, and we can see this stage on failure surface. It is this first stage of fatigue failure, and the second, in the final stage, there was a quick decrease in resonance frequency, and it is this area on the failure surface. And here we can see examples of results of our fatigue research. In every variance, we confirmed that it is possible to improve both fatigue strength and fatigue lifetime for adhesive joints filled by multiwall carbon nanotubes. For best results for adhesive composition filled by 1% by weight, we obtain increase of fatigue strength by about 29% compared to the basic variant. And we also confirmed that it is possible to significantly improve the fatigue lifetime. For example, for this case, for this level of dynamic load, lifetime increases more than 4-fold. And here we can see images of surface from the fatigue tests that show unnoticeable differences in the fractional morphology between the neat adhesive and the nanotubes reinforced adhesive. The material with neat epoxy tends to exhibit a smoother fracture surface than the material with nanotubes reinforced matrix. So we show that it is possible to greatly improve fatigue properties of adhesive joints subjected to peel by use of multi-walled carbon nanotubes. And thank you for your attention.